All right, so what about those higher order derivatives? So it can go like this. Let's say you have a function f of x, and it equals 7x to the fourth minus 5x cubed plus, well, I originally had 2x squared, but whatever, minus 3x plus 4. I'm just making it up, so who knows. All right, so let's say you have that function. So we know that you can get what we've been calling the derivative, but now we can call it the first derivative. All right, using the power rule. Multiply the exponent times the coefficient and drop the exponent 1. Multiply the exponent times the coefficient, drop the exponent 1. You keep doing that. When we do that with a linear term, we get a constant term. When we do it with a constant term, we get 0. That's f prime. So like the important idea here is that f is a function and f prime is a function. So we've done something to one function and gotten another function. That means derivative, by the way, is something called an operator, which means derivative is itself a function whose domain and range are both the set of all functions. So you can think about that while you're trying to fall asleep tonight. All right, now what we're saying is, since I started with a function and the derivative gave me a function, what's to stop me from doing that again? And in fact, I can, and that's what we call the second derivative, or f double prime. And so that's going to be, what's 28 times 3? I guess it's like 84 or something. 84x squared minus 30x plus 4. I can keep doing this. Here's f triple prime, the third derivative. So that is 168x minus 30. All right. Now, what I mentioned before is that when we go to fourth derivative, we're not going to put 4 marks because it starts to get pretty like Neanderthal, just putting 1 mark for everything. So we go a little bit farther in history than Neanderthals and up to the Roman era and use Roman numerals. So this is how we write the fourth derivative of x. And in this case, it's just a constant. And then you can kind of get the idea that, so f5 with a v, so Roman numerals again, that for a polynomial, eventually the derivative is going to be 0. But that doesn't mean we can't take any more derivatives. We, in fact, can take infinitely many derivatives of any polynomial. It just happens that infinitely many of them are 0, right? So that we can go forever. All right. Now, we can also do this. If we say y equals, let's say, 3x squared minus 7, then we have this notation dy dx, right? It's called 6x. All right, so are you ready for the notation for second derivative? D squared y dx squared. You're going to see that all the time. It means the derivative twice of y with respect to x both times. All right, that's what that really means. But you're just going to call it d squared y dx squared, or the second derivative, it's 6. And then so we say the third derivative, all right, that's the third derivative, is 0. All right, so this notation becomes especially important when you do multivariate calculus. So you could be doing the derivative of a function with respect to one variable once and another variable another time. So, all right. We have all these higher order derivatives. Basically means if I have a derivative, I can keep taking the derivative of the derivative, and I can keep doing that for a polynomial until there's 0. Oh, I guess, by the way, let's look at another example. Because, okay, so polynomials have infinitely many derivatives, but infinitely many of them are 0. Is that what happens to all functions? No. So what if your function was f of x equals sine of x? All right, so we now know that f prime of x is cosine of x, right? And then so f double prime of x, what's the derivative of cosine x? Do you remember? Negative sine of x. All right, so then what's f triple prime going to be? What do you think? What's the derivative of negative sine of x? All right, well, negative sine of x is negative 1 times sine of x. The negative 1 I can keep on as a multiple, and then the derivative of sine is cosine. So the derivative of negative sine x is negative cosine x. All right, so then what's the fourth derivative? All right, the fourth derivative is sine of x. The fifth derivative is cosine of x. And so you can see it's cyclical, right? So you're just going to keep going in circles. Negative sine x. The seventh derivative is back to negative cosine x. All right, so that one's just going to go in circles. So what we can say about any polynomial, okay, any polynomial, is that we can say, you know, if if n is the degree of the polynomial, well, all right, and I don't want to use n because I'm going to use n for something else. So what we can say about this particular polynomial is that the nth derivative, okay? So sometimes we'll write f with an n in parentheses to mean the nth derivative. So the nth derivative is equal to 0 for any n is greater than 4. So in general, you're going to have for any polynomial, the nth derivative is going to be 0 for any n greater than the degree of the polynomial. So we see that once we get greater, this is a second degree polynomial, so once we get a greater degree, a greater order of derivative, these are called orders, a greater order of a derivative than the degree, so that would be, the degree is 2, so greater than that is 3, from then on they're all 0. All right, so we can say that about polynomials. So after you pass the degree of the polynomial, all the derivatives are 0. What could you say about sine and cosine? It's a little bit trickier to say something about sine, but here's what we could say. For example, you could say a lot of different things. Think about this. The nth derivative of x, I'm going to say this, is cosine x for n equals 4m minus 3, where n is any natural number. All right, you think about that. And we'll go on to some other before we go on to other things, something that I posted. So we have all these notations that can get kind of confusing with calculus because we have different notations for the same thing, right? dy dx and f prime mean the same thing. F double prime d squared y dx squared mean the same thing. F triple prime d cubed y dx cubed mean the same thing. So we have a lot of different notations in calculus that sort of refer to the same thing, but we use different notations in different contexts. Sometimes they have sort of like implications about things that like they hint things you should be thinking about. Sometimes they're just have different historical backgrounds, but we're stuck with them whatever they are. So I attached to this set of videos today this fine sheet that I wrote up a couple of years ago, actually maybe just last year. It tells you a little about the derivative, and then look at this cool chart I made. So it's going to tell you the function and the names of the derivatives, the notations for the derivatives in 3 different styles of writing, and then some interesting facts about derivatives. So here's a fun fact of derivatives, the derivative, notations, and orders. Feel free to pull that down and peruse it at your leisure and use it amongst your notes.